So, our next and final speaker of the day is Yasin Hamami, currently of the Free University of Brussels, it turns out. I was saying he was from the ILLC all this time. No, I was. He's going to speak to us today about bringing the interrogative model of inquiry to the multi-agent case, a perspective from dynamic epistemic logic.
Sorry, thank you. 1 minute. Okay, so this last talk will be maybe part up to 7, but right. So this is a general project I've been working on several stages, and what I've tried to do is to try to connect or integrate two paradigms that are present in epistemology or formal epistemology. So one is the theoretical model of inquiry, and this has been developed by Handicap. And the basic idea is that you conceive inquiry as a questioning process, so a process of knowledge acquisition or information acquisition. And the second one is dynamic epistemic logic, and so as you may know, dynamic epistemic logic is just a general family of formal systems that are used to represent information and information change in the context of multi-agent systems. I think that there are some reasons for wanting to connect the two that I will develop shortly. And so the main content of this talk is to try to develop a full formal approach in this direction. Okay, so this is the outline of the talk. First, I'd like to say a few words on what the IMI and dynamic logic are. And I would like to argue that there is some kind of complementarity between them which can motivate us to try to integrate them. And also try to say a few words on what type of approach we can have and describe precisely what type of requirements you would like a formal system that integrates the two paradigms should have. And from this list of requirements, then I try to develop a formal system that I call DEL-IMI, and which try to integrate the feature of the two frameworks. So we go from the static, start with the static aspect and move to the dynamic aspect then. And the final sections is something that's touches about inquiry games, because one of the central ideas of the interrogative inquiry is to represent inquiry as a game between inquiry and nature. And so this dynamic system, it will somehow represent the actions of these games. And so it is interesting also to see how we can get from these dynamic systems to multi-agent inquiry games. So all this will become clearly from the first section. Okay, so let's start with the IMI and DEL. So the IMI, this is maybe not so much known, but it's a framework that Jaakko Heintika has worked on for a while, since the beginning of the 80s, and continuously up to almost now. And it's a framework for representing and investigating inquiry, when inquiry is considered as a process of information seeking by questioning. So even more specifically, inquiry is conceived as an index game between two players. One is called inquirer, and the other is nature. So what exactly is this game? Well, in this game, the inquirer is playing against nature, and his goal is to establish the conclusions or to answer a question. So Heintika was really interested in scientific inquiry, and this is, where you can state an inquiry goal in the context of inquiries is that, well, either you want to try to establish a given thesis, or you're just trying to answer a general problem you have. Now, what can you do to reach this goal? Well, for Heintika, there are two types of moves you can do in this type of games. One is interactive moves, and the other interactive move is to think of them as addressing questions to nature. So this is supposed to represent observations or experiments in science, right? So the interactive move is when you have to somehow gain or ask knowledge about the external world, and Heintika think of these steps, like questions and experiments, as questions that are put to the player of nature. And the second type of moves are deductive moves, and deductive moves simply consist in spelling out the logical consequences of the information you already have. Right? So basically, you have a move for getting information externally, information about the external world, and then you have a move which is more of an internal nature, which just consists in spelling out logical consequences of the information you get. And for Heintika, inquiry is really a mixture of this question and information systems. So the literature on that, you have the volume called Inquiry as Inquiry, which grouped all the paper by Heintika up to 1999, and they also published a book called Theoretical Epistemology that's So now dynamic epistemic logic. So dynamic epistemic logic, as I've said, is just a general family of formal systems that are concerned with information change, information change in multi-agent systems. And so what do we mean by intelligent system? Well, we mean systems in which you have some agents, so you represent the information of different agents in the model. But also, importantly, you also deal with higher order information. So this is information that the agent have about other agents' information. And in this program, there has been lots of operational information shared that is investigated. So maybe the most well-known are announcements, logic, or also operations. But people also try to look at other type of dynamic operations, and in particular, questions and inferences have been investigated from a dynamic perspective in the past few years. Because of course you can think of both questions and inferences as dynamic operation of function change, and even more specifically you can think of them as operation of information acquisitions, right? So it's an operation that modifies your information states. So on the side of questions, you have a system, for instance, by Minitsa and Donbenton. We have the DEL of questions. There is more recently an attempt based on inclusive semantics called the inclusive DEL, by Shadei Olsen, and you also have work on physical related questions by Felice and Mayo. On the side of inferences, there have been work by Fernando Vesquez-Quesada in his PhD thesis, so he worked on it in the first days, and also another paper called Dynamic Logical Flowness, in which he tried to investigate what you call this small step dynamic logic of informations, right? So these are steps when you are working with agents that are not logically conditioned. So if you want to know more about these things, there is this book which groups all these, groups different type of operations that investigate in this way by Van Benten, called Logical Dynamics of Information Interactions, and there is a textbook by André Dittmar and colleagues on dynamic implicit logic. So what could there be any complementarity between these two things? Well, I think that's, you have on one hand the IMI that offers you the following. So the IMI, first of all, it is a model of inquiry, which is where inquiry is considered as a questioning and inference process, and more specifically where it is conceived as a game between an inquiry and nature, in which both question and inferences are moves in this game. So it's first a procedure of inquiry, and also the IMI also gives you an account of the interaction between questions and inferences and inquiries. So we see that for Indica, question and inferences are really different rules, but they are really necessarily intertwined in the context of inquiry. But what the IMI lacks is the formulation in the recursion case. And so you can think that this is problems if you want to be interested in social aspects of information acquisition. So if you are, for Indica, for instance, if you will be interested into social aspect of scientific inquiry, well, you will have to move to a recursion case. So this means that we're interested in inquiry processes in which agents can not only play against nature, but they can also cooperate external informations towards a certain goal, toward answering problems, understanding problems, and establishing sets. On the other side, you have dynamic elliptic logic, and the main strength of dynamic elliptic logic is to give you a toolbox for modeling various operations of information change in recursion systems. It's very good for dealing with higher order information. And you've seen that actually you can use that to model questions and inferences, where question inferences are thought as dynamic elliptic operations of information change. But a bit surprisingly, there is not yet a good system in dynamic elliptic logic which is able to deal with both questions and inferences at once. And I think this is a bit problems because some of the people, in particular, think of this dynamic program as an approach to common sense reasoning. I think that's one of the basic aspects of common sense reasoning is precisely to mix this information you get from external sources with inferential steps or combinational steps that you are doing on your own, right? So it's important for this program that we get some kind of system that are able to deal with the two together. This is the first weakness, and maybe another weakness is that, well, there is not yet an application of dynamic elliptic logic to the investigation of inquiry processes. So there has been work on long-term processes, in particular connection protocols with epistemic logic. There is also work on learning theory and dynamic elliptic logic, but there is nothing about processes which consist in asking information, right? So when you have to make an act to gain, to go further or go on your inquiry processes, right? So basically there is no model of iterative inquiry process. And you see that this seems to, somehow these two things could benefit to compensate their respective weaknesses. So the idea of, that I'd like to develop is that, well, maybe you can try to develop a version of the IMI in the recursion case. And indeed, if you want to do that, well, dynamic elliptic logic seems quite convenient because it gives us exactly what we need, namely a way to represent the action of the game, so questions and inferences, when you have to deal with multi-agent context, in particular when you have to deal with higher order information. But if we do that, if we use the toolbox of Dell to move the AMI to the multi-agent case, at the same time, what we should end up is a system which represents both questions and inferences together. And indeed, you can use this discussion of Indica on how questions and inferences interact together to have an analysis, a basic analysis to get this integrated system. And of course, then you can try to get this second line. But for getting this second line, we also need to find a way to define inquiry games in multi-agent context. And you see that this is the last section of the talk. And so here you need to explain how from a Dell system that could represent actions, so question, inferences, inquiry, how you can use it and plug it into a certain definition of inquiry games. So we'll see how this can be done. So now what kind of approach can we have? Well, the approach I propose is the following. So I suggest that we start first by representing the actions of the game in the multi-agent case. So we want to represent both questions and inferences in a multi-agent context. And for doing that, we want to use the toolbox of dynamic logic. So the first step is to provide a framework for representing the intertwined information dynamics of question and inferences, said in a bit way. And basically what we want, well, is presented to represent the moves of inquiry in the multi-agent case. And for doing that, well, we develop a Dell-style system that I call Dell EMI, and which will be multi-agents, and which will integrate both question and inference dynamics. When we have this dynamic system, then we can move to the second step. And the second step is to use this formalization of questions and inferences to define and investigate inquiry games with multi-agent dimensions. And so here the basic idea is that we will use the dynamic system to define multi-agent inquiry games. We'll use the dynamic system for representing both the actions and goals of this game. So we'll see how we can do that. Okay. So now for the first step, we want to develop these dynamic systems. And here is a list of requirements that we would like this formal framework to achieve and represent. So first there are two blocks. First the static aspect and the dynamic aspect. So on the static aspects we want the following. We want three things. The first thing is that we want the system to be able to represent informational states of several agents in such a way that they are able to encode both factual and higher order informations. But what we don't want is that we don't want it to be closed under logical consequence. That's the first requirement. The second requirement is that we need to define what is called the oracle. So the oracle in Hintika is the source of information about the actual world. Right? So the oracle is somehow should be thought as your experimental devices. It tells you exactly what type of information you can access about the actual world. And the specificity of the oracle in this type of context is that the oracle will only be concerned with factual information. Right? It only tells you about states of affairs in the world. It does not tell you about what other agent knows or believes. And then the third thing we want to have, this is a bit for the strategic aspect of these things, is that we need to represent the choices that the oracle and the agent can make when they have to answer questions, right? So inquiry for Hintika is a strategic procedure because when you are asking a question to the oracle, or when you are asking a question to an agent, the agent or the oracle has the choices to provide the answer. When you can show it the answer you will provide, right? So there is a strategic aspect to it in answering questions. And so here we represent at static level the rule for proactive rule for answering that encodes these choices. At the dynamic level, well, basically we want two things at the dynamic level. We want dynamic declaration for questions and for inferences. But now in the multi-agent case, you have two types of questions. So you have agent addressing questions to the oracle. So this would be an act of observation or experiment on the actual world. But you also can have operation of agent addressing questions to another agent, right? So this is when agents are exchanging information between them. So you have two types of questions, but you have one type of inferences, and it concerns, right? So you have last dynamic operation, which represents agent drawing logical inferences from their own information. Okay, so now I will develop the formal details of these dynamic systems, and the basic idea is to try to fill all these requirements. Okay, so first I define what I call the inquiry language of the oracle. So the reason I'm doing that is that you see that the notion of distinction between factual and higher order information plays a role here because the oracle, which is source of information as the actual world, will only provide factual information. And so what I define the language of the oracle E for delimiting what could be the answer of the oracle. And since in this epistemic logic tradition or multi-agent epistemic logic traditions, we always think of factual information as, in a syntactic way, as a formula that does not contain any operators. I just define this language I as being the proportional language. So this is the proportional fragment of the language. We call it E for convenience for what we do later on. And this is the one language we would like to use to model the different things we're interested in. So first there is a K operator. So this is a traditional operator of epistemic logic. And here now epistemic logic, the K operator of epistemic logic, as we know, is closed under logical consequence. So now it's not knowledge, but implicit knowledge in this context. And this read as agent R implicitly knows that phi. Then we have an awareness operator. So we have an awareness phi, and this read as agent A is aware of phi. So you're wondering why I'm introducing these things. Well, basically because there is a technique in which you can have a notion of information, which is not clear logical consequence, a notion of explicit knowledge, and we can define explicit knowledge based on these two things, right? So I'm not particularly interested in awareness in this paper or in this work. I'm using it in an instrumental way to have a notion of explicit knowledge, but only closed under logical consequence. Then we have an operator, which is for describing the information available from the oracle. So we said that phi gamma is true when gamma is in the answer set of the oracle. So basically this means that gamma is the answer that the oracle can provide. So your experimental devices allows you to access information in gamma. And then you have two types of operators for talking about choices of answers. So I would like to say here that the way I represent questions in this framework is as finite sets of formulas. So this is what Kinetica is doing in the propositional case. And the idea is that you have a question is understood as a set of alternatives. And when you have a question, it's gamma 1, gamma q, you are asking, well, is gamma 1 or gamma 2 or gamma k the case? So basically, for instance, if you have a yes-no question, you want to know is Ghent in Belgium, for instance, then this means that you have two possible answers. Ghent is in Belgium or Ghent is not in Belgium. And so these two possible answers, right, you think of them just as a pair. So questions are a finite set of formulas. And the choices of answer, how you can represent it, well, you can simply represent it as a pair when you have a question and you have one of the answers to this question. Right? Okay. So these two operators are there for saying what would be, what answer the oracle addition will provide when we ask a given question. So notice here that questions to the oracle will always concern factual information in the sense that the alternatives, syntactic alternatives, are restricted to the language I. But for the agents, they can ask questions about any formula of the language. For instance, an agent can ask whether agent B knows implicitly or knows explicitly whether P. Right? So you can express these type of things. Okay. So this is a language, and then you have the model. So the model is this Hamami model I'm working with, and it's this tuple with 6 elements. The first aspect is just the traditional model of epistemic logic. So you have a set of words. You have equivalence relation, insecurity relations for each agent, and then you have a valuation function. Then you have the awareness set. So this comes from awareness logic. It has been developed by some people, it's developed by Halpern and colleagues. And basically that what you do is that you associate, for each agent, you associate to each word in the models a set of formulas in the language that represent the agent that the formula that the agent A is aware of at the word level. Right? So this is called awareness sets, and we call this stuff awareness functions. Then you have the oracle. So I represent the oracle in a syntactic way. This is also what Kinetica and his colleagues have done when they have developed interrogative logic, which is another type of formal systems for doing these stuff. And the basic idea is that at each word, you associate a set of formulas in the inquiry language that represent the information that will be available for the oracle at this particular one. Right? So you have to associate a different set of formulas for each different one, because of course the information that the oracle can provide should change on this different word. Because if you want the oracle to be veridical, you don't want it to give it P in a word in which P is the case, and P in a word in which negative is the case. Right? So you have the oracle for each word in the model. And this is the answer of the oracle. Then you have the representing of choices of answers, so you have them for the oracle. And again, it's again the basic same idea, but it's nothing ridiculous. So for each word, you associate all this set of these pairs that represent possible choices of answers for all the different questions, and you do the same for the agents. Okay. So with this, so then there is the semantics for these things. So the semantics for the epistemic logic fragment, well, just the semantics of epistemic logic. I imagine that you've probably all seen this. Then there is the semantics for the oneness operator. So this is what as follows. You said that phi is agent A is aware of phi at all W if phi is in the subset of agent A at this W. And then for the oracle, you follow the same idea. So you said that when phi gamma is true, so gamma is available answers from the oracle at all W if gamma is in the subset of the oracle at all W. And you follow for the choices of answers. Well, gamma I is possible choices of answer of these questions at all W if this pair is contained into the parameter for answering phi, and the same for the agents. Okay. So with all that, I think we have the basic setting for the three requirements at the static level. So first we have a notion of information that is not close to logical consequence. But here we have to make further steps. So from implicit knowledge and the oneness, we define explicit knowledge. So basically that explicit knowledge is just the combination of implicit knowledge and the oneness. So you said that the agent A have explicit knowledge of phi at world W. If he has implicit knowledge, and if he's aware of phi at world W, and if he's aware of phi in each word in this specific range. And you see that this is blocks logical options because oneness is not close to the logical consequence. Right? So if you ask for explicit knowledge to be aware of it, then you have a way to limit, to block the closure under logical consequence. So there are some additional properties I'm putting on these things to get the infinite class model. The first one is the coherence property of oneness, but it is that on the epistemic merge of the agents, the oneness set should be the same. And the second one is the oneness of validity. So this is an idealizations, which may be strong idealizations. And we'll come back to it, but basically what I asked the agent to be aware of all the valid principles in the language. So this means that each agent knows what follows from what. So it knows what formulas follow from what set of phrases. Okay. So this is the information of the agents. This is the oracle. So we've already seen that. So we represent the oracle by saying to each W another set. And we have two requirements on this oracle. First, we want it to be truthful. So oracle always give true answers. And so this is a requirement on this oracle functions. And we also ask coherence property, which basically says that the informative power of the oracle on the epistemic range of each agent is uniform, right? So the oracle cannot give you a lot of information at a given word and nothing at another word, right? It's there is a way to say that the oracle should be somehow uniformly informative. Okay, so this is the second requirement. And for requirement was this choice of answers, so we presented the choice of answers by associating these pairs to each word models. And here there is only one requirement, is that when you have a given models, you just ask the agent to have one unique possible answers. And so this you might be wondering what I'm doing with these stars, because I want to have games in which there will be choices of answers. So then there will be a trick. So this is for describing what happens at the level of epistemic change. And when we go to inquiry games, we'll abstract from that to record these possible choices. So here I'm not showing you but in the paper there is all these things give you an identity class of models, and you can axiomatize this these static fragments on the level. Right? So basically here we have all static level and we have all 6 requirements. Okay. So now you can move on to the dynamic aspect. So the dynamic aspect is really what is essential. You want to represent both questions and inferences as dynamic epistemic progressions of information change. So we start with questions. So maybe you know that in this dynamic modeling of epistemic phenomena, when you have a dynamic epistemic progression, you want to capture, you can do it using 2 aspects in the formalization. So one is the operations on the underlying models, right? So how is your operation going to modify your static level of representation of informations? And the other one is the preconditions to this operation. So when are you are you able to actually do this operation? And here I would like to use these 2 things, operation on models and preconditions, to capture different aspects of both questions and inferences. So first we start with the agent to oracle question, right? So when the agent is asking a question to the oracle. First thing we have to do is, well, how is this going to modify the underlying models? Well, first let's look at the input. So when an agent asks a question to Oracle, there is an agent A that has been designated, which is asking the questions, and there is a question Q0. Okay. And what's happening? Well, the suggestions I would like to propose here is that we think of questions as conditional operations. So basically, when you ask a question, the information you will obtain is depending on the information that the source of information has. So if the Oracle has the answers, then you expect it to give it to you. And if the Oracle does not have the answers, then it will just stay in the same existing state. So this can be captured by having two clauses on how a question modifies an underlying model. So the first clause said that, well, if there exists an answer in the question, so that this answer is in the answer set of the Oracle, and this answer is legitimate somehow with respect to the priority for answering of the Oracle, then the model underlies information update with the answers. So I'm working here with an update that's what I call explicit information update, and indeed it's the combination of traditional what we call a high information update, meaning that we eliminate all the models that are incompatible with the formula gamma I, but it also modifies awareness sets in the sense that it adds formulas to these awareness sets. So basically, this is just a version of hard information update when you are in the context of explicit knowledge. Right? I can explain it from. There is nothing. Okay, so under this condition, then you have the model underlying high information update, and if there is no such thing, so if there is not an answer that the Oracle has the answers, which is in accordance with right answering, then the model is left unchanged. Basically, you don't have any information. So then you have semantics of this Oracle question operators. The semantics say that phi is the case after question Q0 has been asked by agent A to the Oracle phi. If and only if under the preconditions, then phi is true in the updated models. And so what's important here is the precondition. So the precondition here is a nice way for encoding a central aspect of questioning in Hintiga's model. So for Hintiga's model and in Hintiga's theory of questions, when you want to ask a question to be legitimate in asking questions, you need to establish a presupposition to the question. So a good example of presupposition, for instance, in the first order case, is that if you want to ask who killed Kennedy, for instance, a presupposition is that you need to know that at least someone kills Kennedy. Right? So this allows you to meaningfully ask or legitimately ask the question. When you are dealing with these just propositional questions, or these standard questions, the notion of presupposition is simply the disjunction of the answers. Right? So you are legitimate in asking the questions if you know at least that one of the disjuncts, one of the possible answers is the case. So this is what Hintika is doing in theory, and so this requirement that you need to know that one of the formula, one of the answers is the case, can be thought as knowing that the disjunction of the formula is the case. And since we have explicit knowledge in a model, we can simply express this precondition by saying, well, the agent need to have explicit knowledge of the disjunction of the possible answers to Q0. And this precondition is a precondition to this question operation, right? So we represent both notion of presupposition as well as the preconditions, and represent the aspect of question as request of information, right, under this idea of conditional update. The agent-to-agent questions follow exactly the same, follow very closely the same idea, right? So you have now two agents. Agent A is asking question to agent B. He can ask a question that contains any formula in the language. There is no restriction to factual information. And the operation, the operation is the same. So you have a conditional operation, but now the sources of information is not the same. So before, the source of information was the Oracle, that's what you can learn about the actual word. Now the source of information when you are asking an agent B, well, is simply the explicit knowledge that this agent has, right? So this is how we represent in this model information of an agent B. So the condition here is that for having an answer, for getting an answer with I, and before updating the model with I need to be agent A needs to have explicit knowledge of I, so first requirements, and I has to be in accordance with this correcting rule for answer. When this is the case, then you have an update with I, otherwise the model is left unchanged. Then you have the semantics. The semantics is exactly the same form as the question operators. The only difference now is in the precondition. So in the precondition you have explicit knowledge of disjunction. So here it's exactly the same idea, except that in the disjunction you can have any formula for I, so you are not restricted to factual information. Okay. So So we have questions, agent record question, agent record questions. Now we deal with inferences and logical inferences. So at the level of the operations, the logical inferences, there is nothing much that I would like to present here. So basically, what's the effect of an inference is when you can do one? It's simply to gain explicit knowledge of the conclusion. So as an input of the inference operation, you have the agent doing the inferences, you have an inference represented as the conclusions, and the set of premises psi1, psi m. And when you can do an inferences, well, what does this amount to in this context? It simply amounts to an explicit information update with the conclusion. So this means that when you will actually do inferences, then as a consequences, you will have that the agent have explicit knowledge of the conclusion, which is what you would like to have. But of course, this does not represent much of the inferences. All the burden of it will be at the level of precondition. And here you have the precondition. So you have now a precondition is a bit more complicated. So if you want to be able to draw inferences with psi, what do you need to do? Well, first you need to have explicit knowledge of the premises. And so this you can represent in this context by having a conjunction of explicit knowledge for all the psi I, which are premises of the inferences. But you also need to have explicit knowledge that the conclusion follows from the premises, right? And this you can express in this way. And this is the reason why I put all the valid principles in this logic inside the one set, because I want the agent to know exactly what follows from what. So you might say that, well, that this is a strong generalization. It's a strong generalization in the sense that in one step, the agent will be able to make a very long proof, right? But what is important here is that indeed the agent has to make a step to get the conclusion. This is in this sense what is not idealized. And if you want to counter this idealization, what you have to do, well, there is an easy way to do it. Simply add additional operations that mimic somehow what you would do, for instance, in a natural reduction system or in a sequence calculus. But this, in this context, doesn't add anything. You just put a very branched set of syntactic treatments that are not very interesting. And of course, you also you can add additional hypotheses on these consequences, and you can restrict the steps that the agent is making to a small step. If you want. This can be done by adding extra requirements on the IMA models. Okay. So at this step, I think we have all the elements we wanted for the dynamic system. We have information of the agent, that includes the logical consequence, we have representation of the record, and we have representative of choice of answers by the agents. And at the dynamic level, when you have a dynamic elliptic operator and operation for agent addressing questions to the record, dynamic operation for agent addressing questions to other agents, and dynamic operation for agent drawing logical inferences from normal information. Okay. But at this level, what we have, well, basically we have the actions of missing query games in the mutation case, right? We know what exactly is the effect of asking questions in a mutation context, and what exactly is the effect of drawing inferences in the mutation context. But if you really want to have an interconnection between these two paradigms, you need to provide a definition of inquiry games. So now, how can we pass from these dynamic systems to multi-agent inquiry games? Well, first let's remind us what was Unica inquiry games. So Unica inquiry games was two-player games when the goal for the inquiry was to either establish conclusions or to answer a question, and the actions were drawing logical inferences and answering questions naturally. And so the question is, how can we use dynamic systems to define mutation inquiry games? And here we can use recent work in these directions. So in particular, there are two persons, Hans-Van Ditmarch and Thomas Agotnes. They have looked at that, and so they are wondering how can you define games when your actions are dynamic elliptic operations. And so what they propose is a way to define games when you have the goal is represented by the goal formula in the dynamic elliptic systems you're considering, and the goal formula that the agent would like to become true. And the action, they are the dynamic epistemic operations. So they did that for public and logical games and question-answer games, but in these two cases, actually they did that at the level of strategic games. So this is just one-step games. And of course, one-step games doesn't make much sense in the context of inquiry. So we have here to try to find a way to use this ID, but bring it to the extensive game level. So there is a bunch of references on that, and there are a couple of papers. Okay. So this is my strategy for trying to reach agent inquiry games. So this is really the this work on channel equations is really the beginning. So what I have here to propose are mainly the definitions, and further work will have to try to investigate further these technical properties. But for defining this multi-agent inquiry games, I would propose that we go in 2 steps. So first, we define inquiry game trees that actually represents all the possible inquiry paths that the agent can do. So there is some technical presentation of what it is, but I'll just explain it very briefly. Domain ID, because technical is not so important. So the basically is that you can represent a state into this game as a given state of information, and you can do that by taking one array if order, which encodes the information that the agent has, and you also have to designate a word that will be the actual word. Right? Okay. So this is a given epistemic situations. Now according to Critica, what an agent can do, so if you consider agent A, what agent A can do, well, it can do 3 things. Now it can ask a question to another agent, it can ask questions to the oracle, and it can ask, it can draw logical inferences, right? These are the 3 types of things it can do. Now we want to define the trees that encodes all these things. Okay, thank you. We want to define the trees that encode all these things. So what are the branches we have for the question asked with the agent? Well, we have, sorry, I replied with the inferences, which is the most simple case. So when an agent is drawing an inferences, what's going to happen? Well, we're going to reach another epistemic situation. Right? This is what happens. And what you want to define in your trees is, well, in which case do we have a child like that? Well, basically, you have a child like that in your tree, to this node, if the precondition of drawing these inferences is satisfied here. So if the precondition of drawing these inferences is satisfied here, then you have a child. And how do you obtain the child? Well, you obtain the child simply by applying the dynamic epistemic regressions, right? So preconditions of inferences, they tell you when you have a child, and the dynamic epistemic regression tells you, well, in which epistemic situation you will gonna end up, right? In which inquiry node you will have to handle. The case of questions is a little bit more complicated, because questions, on the strategic level, it's a 2-step thing. First, you have the choices of the question you can ask, right? So there will be as many branches as questions you can ask, or you can legitimately ask. And then, when you're getting there, so you have to ask a question to a given agent, but you are not yet into an epistemic situation, because then there is another strategic choice, which is the choices of answers. So basically, when you ask questions, you end up in a situation when you have put it on the table a question A, and you have to make precise that agent A asks question A to B. Right? That's basically. So the question in this inquiry trees, there will be in 2 steps. First, put the question on the table. So for instance, ask agent A ask question QA to B, and then you have the possible branches that the possible way that agent B can answer. When agent B answers the questions, what you have, well, you again have epistemic situations, which corresponds to the model that obtains by updating the answers, right? So this is the basic case. So in inference steps, you have 1 step, and you get to the inquiry nodes. Questioning steps, you have first put the question on the table, and then you have another branching step with all the possible answers. So depending on the answers, you end up in different epistemic situation. And of course, the same idea is that you can ask your questions only if the precondition is satisfied here, and you will use the dynamic operation at this level. So there is a trick, as you may guess now, that there is a trick to get the right set of answers here, because we have encoded into our model the choices of answers, and the trick is to slightly play with equivalence classes of models when the equivalence class is therefore abstracting to these choices, right? So we go up the level of abstraction, and we take classes in which we model one epistemic situation, but we less the choices of answers to vary. So there's a small trick to do that. So basically now we have the tree, and the tree tells us exactly all the possible paths that the agent can take, and tells us exactly what's the epistemic points you're going to end, or the epistemic situation you're going to end. Now if you want to define the word game, so a game, what you have to start with is a given epistemic situations. You have to make precise the depth of the game. So how long do you want your inquiry to last, because this is quite important in this context. And then you have this famous goal formula. So basically you have to associate a formula in the language for each player player being the agents and the record. And this formula has bandit match, and as I said, it's the formula that the agent will actually become true in the game. So this is how you state the goal. So how is this game defined? Right, you have a set of players, which is a set of agents and your record. You have the inquiry game tree, right, which encodes exactly all what you can do in the game. Then you have your player functions, so there is not much restriction of your functions. When you are at the node, any agent can play, but of course your record cannot play because it only has a passive board and you answer questions. But if you get into a questioning node when the question is on the table, then the player functions tell you that, well, it's basically the person or the agent to whom the question is asked that should play at the stage, so either the oracle or the agent B. And then you have this utility function, so this is just the same idea. So you have utility function at the node. Node for player P is 1 if the goal formula of P is true in its selecting node, and 0 otherwise. Okay. So So just to maybe just want to illustrate that this goal formula allows you to represent both the requirements of establishing a conclusion or asking a question. So if the goal of agent A is to establish formula phi or satisfy, well, basically the goal formula is that at the end of the day, the player R wants to have exponential phi. So this is the way you can express the goal. When you want to ask, you want to get an answer to a question of this type, well, you can express this requirement of knowing the answer by a disjunction to tell you that, well, you basically need to either you know answer 1, or you know answer 2, or you know answer n, right? So this shows you that this technique of goal formulas, it allows you to present the type of goals in Technica, either establishing a thesis or answering the question. And okay, so there is a notion of strategy. There is nothing here. It's just the traditional notion of strategy for extensive games. But I would just like to say a few words about inquiry games with multi-agent features, because you might say, okay, so why do we would like to have inquiry games with multi-agent features? And I think that there are two main examples that are quite important. The first one is what I would call social inquiry games, and this is the context in which you have a group of agents playing. So here you might have to want to investigate different types of phenomena. So for instance, you might be interested in several agents cooperating together towards a certain goal. If you want to do that, then you can express that by having as your goal a given formula that will be common to all the agents. But you might also want to look at a group of agents that are competing with each other. So for instance, here you can you have two players A and B, and this will express the requirement that, well, agent A wants to know the answer to these questions, but at the same time, it doesn't want B to know at the end, right? So you can have these more complex requirements on a group of agents. So social inquiry games, I think they are important if you are interested into this cooperative or adversarial strategic aspects of inquiry. The second one is when you are second type of inquiry games where multi-agent feature plays a role, in when you are interested into this higher order information. So I think in the community of Dell and mostly strategic interactions, higher order information always play a role, because when you have to investigate different types of functionality in this context and decisions making, then it's also important to know what other people know and that you're making decisions. This type of information plays a role in the way you are making decisions or the way you are choosing strategic decision moves. And here you see that since all the models have been developed using a language of multi-agent epistemic logic, basically you can express goal in which you have higher information. For instance, here your goal is to know something about what agent B implicitly knows. So here agent A would like to know whether agent B implicitly knows that agent A knows B, so you can claim this type of thing. So this means that you can have a requirement of your inquiry statement that concerns higher information, what other people knows and believes. And the actions, well, again, what is nice is that in the actions you have both questions and inferences with multi-agent features. And so you can represent the inquiry processes in a very natural way compared to what, a very natural way following what they want to represent, namely various type of information change when you have this higher order type of information. Okay. So this is just a conclusion. So this basic idea of what I've tried to do here is start with observation that might be complementarity between TMI and Dell, and that you might want to connect them. If you want to do that, I propose a two-step approach. for integrating them. The first step consists in developing a system that will represent both question inferences in the mutation case. And then the second step would be to use this modeling of actions in the equagrams or root equagrams and use it to define multi-agent equagrams. And I think further works might be to try to investigate further these multi-agent equagrams. Okay, thank you.
And now we have a couple of commentaries. First up, Xavier.
So thanks again for your paper. So the advantage of this paper was simplicity clarity. So thanks again for the very clear presentation and analysis of the different concepts. But so I have a couple of notes about this paper. Two sorts of notes to say about the so-called philosophical logic or philosophical logic. So the first is about the methodological features of your system, for instance, it's technical. And the second sort of questions has to do with the capacity of the system to address problems in philosophy, because there are a huge, of course, of application of the system. So I have a lot of questions, but I want to be very clear. Just 4 sorts of questions, okay? So maybe you prefer to give an answer after each question to give as a package, or?
No, then ask one question.
Yes, I think it's better. Okay. So the first is about the very complementarity between DEL and IMI. So we said it's possible to have a complementation between both systems in order to integrate them to one is the same. So my question is very nice. So is why should there be some methodological reasons to be very cautious about the integration of both the two systems? Could there be something like inconsistency when you want to integrate both, or is it just a question of being no one has done this in the past, but it's very simple and feasible? What's your position on this?
So there has been systems for the IMI. So Henika and colleagues they have developed a logic that tries to model that, and it's a logic based on basically it's a tableau systems when in addition of making moves in the tables, you can add additional premises by asking questions. But this is a syntactic way for doing it, and this syntactic way it actually runs into problems when you deal with higher level information, because in higher level information you have things like, for instance, you might at some points you might know that agent A does not know phi. So if you would be syntactically speaking at this stage, if you have just if your information state just a set of formulas, because that isn't what you know, you will have this into it. But then if B turns out to know phi, then you are just losing this knowledge. Right? So this is a purely syntactic approach. When you go to higher information, is a bit tricky. Because basically, if you like to do it syntactically, you need to have some kind of revision mechanisms that tells you, okay, you're not really cumulative, but given the new information, you will have to withdraw some new things. Right? So for instance, if the agent C say announce phi, say phi, well at this stage you cannot know that B does not know, because at this stage he should know if I had the transient, right? So you have these revision mechanisms, and I think that is very good for it deals with that very easy, automatically. Right? You just erase the words and then you get expected results somehow. So when integrating the two, at the meta-logical property level, I would say the solution of Henika works finally in the factual case. You only have when you have a cumulative process of acquisition. But when you go into this, when you bring higher information, and you just need an additional mechanisms for treating it. And the way I propose it uses semantic way of doing that. Right? So this problems of non-cumulativity somehow is somehow an issue that first organization of the IMI will run into. And so that you need a new way to do it. That's one reason. Otherwise, you might expect that, well, basically, as I was saying, there's logic of questions and logic inferences, so that you really can, it's just a matter of putting things together. Well, basically, it is a matter of putting things together. The only difference is that all the logic of questions that have been developed so far, they have already been developed in the logical relations case. So that they have a way of treating questions on a set of missing words but they don't have questions in which you are dealing with this weaker version of information, which is not called logical human issue as an ontology.
Second question has to do with logical science, because in the paper you say that it's very clear that you need a system in order to give a question-answer game with non-logical innocent players. But in the paper you just give some references about this point without mentioning exactly the way by means of which you can block the logical science. Hence my point. Can you avoid logical science by means of the awareness operator, the A as in F agent helper, or by doing the difference between implicit and explicit knowledge, or both?
So the way you block logical conditions, because you have explicit knowledge of phi, and basically it's equivalent. There's many formulations, but you can this way different one. But basically, the one set is not close to logical consequence. So for instance, you might just have in your one set, you might just have P, this at a given stage, and if this is you have just one word, P is true of this word. When you have knowledge of P, explicit knowledge of P, but this is the only things you have. Because for having explicit knowledge, you need to have a oneness. So it depends on what you have in your oneness set. Right? So this is the way you block logical omissions. Otherwise, you have also P and P, and if you have P, Q, or P and Q. As semantic knowledge, you have lots of stuff. But the oneness, just say, okay, this is just blocked to that. And then when you want to redate, you can just add things here. And when you are adding things here, it makes you small step if you want on the key. And just what's interesting of the oneness, it's again for the same idea of cumulative things. It's because since you have these two conditions, you could be aware of, as the first example, that name, for instance, that agent B does not know phi. So you can be aware of that. But if you have an update and this turns out that now you don't have explicit knowledge of that, then you're losing explicit knowledge automatically. Because for explicit knowledge, you not only need it there, but you also need it true at the level of the operator implicit knowledge problem. So that's how all these things work. That's basically. The interest of the oneness that is for dealing again with these tricky cases of higher order.
So maybe I have to condense the two last questions because another commentator is supposed to be the same. So just two very speculative questions, sorry in advance. The first is about different social inquiry games. You said there are different games you can play outside science, let's say, because we can apply the system to rational agency, epistemology, philosophy of science. So just first question is, what about, is it possible to construct a tableau method or semantics in order to explain exactly rationality in poker, for instance? If you want to play poker, are you able to make the difference between the oracle and the higher order beliefs or higher order knowledge? Sorry, because if you have the oracle, you are supposed to give the truth. But if you play poker, for instance, if you want to bluff, so how to make the difference between the higher order knowledge and the factual information in knowledge? And the correlative question is my last one. So it's about anti-realism. So if you are an anti-realist, for instance, what is the status of oracle?
Right.
That's all.
So I would say that, so here you can play, so you see that there is, the choice I've made is the most simple one, just to use an extreme explicit knowledge that's based on epistemic logic. But there is many ways you can present information. So for instance, in the case of poker, you would have to do something more weaker. For instance, you might want to deal with beliefs, right? So you might not want to have knowledge that implies truths, but you might just have belief, and there are many logic you can use in this field to deal with that. So if you have beliefs, then the belief does not have to be true, right? So you can update your information in the poker games. People are lying. Basically, you get some beliefs based on their lying. Lying is a very complex task. But basically, the thing is that you might go into weaker form of information in which the agents can give information, but this information that does not have to be truthful, right? So if you want to do that, you need to work with other models. For instance, here there are many models of presenting stochastic logic in many ways. With a solution. If you are an anti-realist, I would say maybe you have to go towards justification logic.
Yeah.
And right, so maybe find a way. So then you, so you can also work with justification logic. So then all these different issues, the concerns. I think that's, I mean, my point of view on these things is that both questions and Francis they should work with different types of epistemic attitudes. So there could be questions when you have beliefs, there could be questions when you can get justification. And so it's a very general scene that can be investigated on this different level, right? So you can take any base representation of information, for instance, belief or justification, and on that you can try to say, okay, how should I define the notion of questions so that it modifies my notion of information? And you can play with this idea, I think, on many types of logic. I think it would be interesting to do, in particular, to see what type of questioning phenomenon cannot be represented in one cases, but can be in others. For instance, the case of poker, we have to go towards weaker things. The case of naturalism, we have to go for weaker things. You can also think about probabilities, for instance. That's another way. Also, algorithmic knowledge is another way. But basically, the main idea would be, okay, start with a static level of information that you want to choose, and then try to figure out how to resolve questions and modify this type of information.
That's all right. Thank you. Thanks.
I don't quite have as much, but let me try to ask you first about the motivations for this, because if I understand this correctly, I mean, it's complex. So you're able to represent a certain kind of uncertainty, but it's not like this gives us any tools for solving problems, for instance, or predicting optimal behavior or anything like that. It's only for representing a big tree of possible things that ways things might play out, right?
Right. So you're right. So I think it's just a two-step thing. So if you want to investigate strategies for solving, first of all, you need to start with representation of information. In this case, that would be the first steps. And strategy, the investigation of strategy, or for instance, concepts, existence of social concepts, or algorithmic property of finding strategies, this should come next toward investigating this multi-agent inquiry games. Right? So that's the next step.
Okay.
So the first step would be to do that. Then I would agree. I can even advance the criticisms from myself. I think that this might be, my opinion is that this might be too loaded for having a good formal investigation of that. So maybe the solution would be to try to look at iterative games in a simpler case, in such a way that, or in a more abstract way, in such a way that you can then use it to apply to a system like that. Right? So that might be that you might divide labor again in different ways, not just start with inquiry games in this way, but try to see, okay, what's really general about inquiry games, and I think this structure of branching is what seems to really matters, and this form of information. Maybe take that, try to prove things at this level of generality, and then transfer the results to this mutation. So I think there is a methodological issue here for these next steps that you are suggesting here.
Okay.
But this is what is for Hendica. To be frank, for Hendica, this is what is important, right? So Hendica think of inquiry as a game because we think of it as a strategic process. So that means that asking a question, choosing a question to ask, is strategic issue.
But Hendica usually only talks about me, the scientist, talking to nature.
Right.
That's a very simple kind of game, which this would be overkill for.
Well, then, so that's the whole motivation for the work, that if you want to do these other things that need multiplication aspects, then, I mean, for handicap, this is an overkill.
Yes.
But then it's an issue that I don't know if how handicap wants to take social process in account in this view of something inquiry. So I had a discussion with a couple of people here. I still don't know exactly what Hendica's views on that. So there are some people who think that, well, the social aspect of inquiry doesn't matter. For instance, even if you go to learning theory, you don't see much of the social aspect. You always still have this one agent, which is pretty algorithmic and these kind of things. So there is a philosophical foundation, so whether you consider social aspect to be important. Then independently of that, you can think of this as purely grounded into the Dell tradition, and then into the Dell tradition where it's very clear that the social aspect of all matters because this is what we're interested in primarily, and so then this gives you motivation for going further in this direction.
Okay. But one thing that makes me a little bit confused about the motivations is that this this relates to the poker question as well, that this is somewhere midway between, like, in one extreme you could be handicapped, right? And you could only be interested in a single inquirer whose purpose is to acquire as much information as fast as possible from a nature whose only move is to respond truthfully. That would be one end of the extreme. The other end of the extreme would be to have something like a Hamami type game model where you explicitly place utilities or other kinds of preferences on the agents, and then you model the collective, like the information and preference dynamics, which will play a lot together. But this seems to be a sort of midway between those two things, because you have truthful players, but yet lots of them.
Yeah. I think I really think that this idea of as soon as you think of the questions as conditional operation, you can just put whatever you want here, because basically if you have another dynamic operation which changes the information in one way, just fit it into what does it mean to give an answer. Basically, giving an answer is always announcing the answer, and so if you have a logic, you can always have a question saying, well, under this and this condition, the guy can answer the question. So moving the models towards different form of interactivity is not so hard, because basically, as soon as you have the good dynamics for it, you can get the question operation.
Right, but your description of that dynamic would blow up as you had more realistic behavior.
So
right?
what do you mean by blowing up?
Well, I mean that would be very, very complex to specify in this kind of language. For instance, if you would encode something like my strategy in poker into this format, it would be very, very big, wouldn't it?
So no, you do not. So what do you mean by encoding the strategy? You do not encode the strategy at this level. You encode just the information that the player has. Biologic for talking about strategy, but the strategy is just another object, another formal object. Then you plan when you are all this sort of defined. You have your inquiry games, you have a tree, and then you have your games, and then you have strategies as in your plan, the functions. Function that tells you each time this is a given player to play, what should you do. Yeah. So strategy is not represented at this level. And the interest of these dead models, if I want to define them a bit, is that they are very good to deal with complex phenomena, because you can feed them with very complex formulas, and they just adjust themselves for telling you what exactly becomes true afterwards. So, for instance, the reduction axioms for weak announcement, it's a very compact way for something which is quite complicated, because you have all these phenomena, strange phenomena of revision that are going on that are empty.
Yeah. Okay, but another little complexity reducing question that I have is, well, as I told you, I really like more pictures, because I don't like letters. But could you go through like the simplest possible example of how this inference process works? Like if I implicitly, or like let's say I explicitly know that P and P implies Q, but I haven't yet realized that I know a second third thing. Well, how would you represent this, and what's the process?
Okay, so you just have we have just one word in which P is the case. So you have the one asset at this word W. So here you have okay, you have P and Q. So you have P and P implies Q. Then you just have this non-merge, this is the one word asset in which P and Q is the case. That's the word W. So at this stage, you have the explicit knowledge of P, because you have implicit knowledge of P, and you are aware of P. You have explicit knowledge of Q because you have semantic knowledge of implicit knowledge of Q. You have implicit knowledge of P implies Q because P implies Q is true here, and it's the one but you still don't have implicit knowledge of Q. And so basically what you do, and this is an operation I have not developed, but you are when you are making the inferences, you are erasing the word in which Q is the case. So since here I just one word, nothing is changed, and you are adding Q to this one set. So you have E implies Q, and Q. So at this stage now you have explicit knowledge of Q, because you have explicit knowledge of Q and Q where so that's the step you're making. And so the precondition for doing that is that you need to have explicit knowledge of P and P plus Q, and you also need to have explicit knowledge that P somehow P and P plus Q implies Q.
Right.
And this stuff, it's on the hypothesis set that you have one as valid principles. That's an assumption I'm making for making this in more transition.
Okay, so that's fair enough. But what kind of like object, or what's the recipe, or what kind of data structure represents which of those many things that you could have done with user link? When you say, I mean, one thing you could do is say, I want to perform all inferences that are possible given my current explicit knowledge, but here imagine something more specific.
It's at the level of your progression.
Yes, and how do you represent
So
it?
when you do
Like
that,
if I want to say, like, suppose we have some person who has P implies Q, P implies R, P implies S, P implies T. This person does not like realize like rings in the water everything at once, but I want to encode or tell the model somehow. Now this person realized one of them, and one of the consequences of the document. So how are you going to tell the model that, or how are you going to encode that?
So I think what you want to somehow what you want to do is restrict the power of the agent. You cannot do any inferences. So you cannot do this chain that you want to do that. You would like it to not do. Well, for doing this chain, actually, you have to do this chain because you have to. Well, he doesn't have. But what you can do is at the level of the valid principles you are making, you are putting all the logical consequences under the form of implication. But at this stage, you can say, okay, now I'm just considering consequences of this form. So you don't have to put the whole logic basically into that, but you can put restriction on it. Okay, I'm just doing one-step deduction in the Hilbert systems. I mean, the consequences of only one-step deduction in the Hilbert systems, right? From some premises and a conclusion.
You're just looking for anything that matches a specific inference pattern, for instance.
Right. So you could do that. So I think the restriction is at the level of the assumption, and I think it gives you it should give you the right results. So actually, this is completely independent of the morphing. I think in the sense that if you modify what you consider to be a consequence, what you write. So inference are represented like that. That's the premise and conclusion. If you just put some more restriction on what you want to do here, this will automatically generate constraints on the first you can do, and it will generate constraints on the true. Because since the precondition is that you know the implication, if it doesn't know sufficiently enough, that's a complicated stuff for other complicated stuff, then it will not occur. So
there's a couple of things about this that are funny, like should you start?
Well, just if we take a couple questions.
Yeah, let's do that.
Yeah, so then wrap up for the day.
Could I add something to Mateus?
Yeah.
Is the awareness set just a list of formulas that you're aware of?
Yeah.
It has no semantic representation in terms of it's just a list of formulas.
Yeah, there begins the funny. That's what I'm saying.
Yeah. Any other quick? Okay.
Okay, so here's my general question. I heard it in some of the other questions, which is I always ask this when I listen to talks like this, and it's not meant to be hostile because it's not. It's informative. But what's happening? What are you? I can think of this dynamic epistemic logic as stating in a precise way what we do, or what societies of us do, what we should do, right? That's often the goal of logic. Normative view, I don't know whether you think we should do these things. Or an actual language that now moving to artificial agents, an actual language that you could attach a derivative to, and little multi-agent systems could run by doing derivations in this language, or a specification language that could be used to state what a good bunch of multi-agent systems are doing, whether they use this system to do it or not, or someplace else entirely.
That's a very fair question. I share, and I think I understand the different instructions, and I share the content. So I think if you really want to make sense of that, what makes sense to me is to use, so here you are using logical methods, but just for modeling information. So you are using logic as you use information theory, and theory, as you use logical methods. So it doesn't have, so when you say the pure logic, whether you want to have it in a normative, descriptive way, you want to use it for improving, or you want to satisfaction problems. Theoretically, you're using logic as modeling tool, not less, not more. So now if you are asking, well, are there issues about normativity here? Well, there are issues of normativity because this describes how things should change under certain circumstances. And this changes when you cannot do whatever you want, right? There are restrictions on it, there are norms on how, for instance, explicit knowledge is acquired. Right? So when you say, okay, when I get gamma, I'm just emulating words about word in which gamma is not the case. Well, this is just one normative way of considering. So this is somehow the norm of considering it this way. So at the level of the logic, my answer is well, purely modeling tool. Some of the people think differently. People are doing serial improvers for dynamic logic. They are also interested in the computational properties of these things. That's fine. I think the main advantage of it is in these games are modeling information change. Okay. That's the first one. Second point is that there is an issue about the strategy, what we should do in a strategic sense. And this is what is really interesting in query for Hinika. So that's a question just putting it in another environment. But basically, Hinika is really interesting in saying, okay, if you are interested into these inquiry processes, and he says the same thing for logic, he says it's not only, it's good to explain what you can do, that's fine, but what is really important is that you should tell me what I should do if I want to progress in my inquiry. And here, I hope that game theory can give some answers to that. So Hinika has never applied, used, and it's shouldn't before into his models to have the precise game theory formulations, and then to say something as game theory researcher would do. But I hope you can. There is a few steps to make, but I hope these steps should. I think these steps should be made because we can probably learn quite something about that. So there is a strategic level inside the model. But I think I'm sharing some I'm using as modeling tools as my research.
And so I'll give the final question to Deirdre. No? Anyone else take up that spot? All right then. Let's thank.
You know about this op-coin problem, where you have the